Dear students, in today's video we are going to discuss electric field intensity due to infinitely long straight uniformly charged wire, right? We will calculate the value of electric field intensity produced due to an infinitely long straight uniformly charged wire. So here important thing to understand is that the wire has infinite length. Suppose that L is the length of the wire and R is the distance of observation point from the wire. Then it is having infinite length because this L is extremely large as compared to R. The second thing is that our wire is uniformly charged. What does this mean? This means that the spread of positive charge is same throughout the wire. It means that the electric field produced due to this wire is uniform. Now let us first of all define the Gauss law, because we are going to implement the Gauss law for calculating the electric field intensity. So first of all we define the Gauss law. Gauss law is phi E. Here phi E represents the electric flux. It is given as surface integral of dot product of the E vector. E vector is the electric field dot ds vector. Ds vector represents the area vector is equal to q. Q represents the total charge inside the surface S when it is placed inside the vacuum, divided by epsilon naught. So the surface integral of the electric field produced by any source charge over any closed surface, right? So Gaussian surface is there. So whenever you are going to implement the Gauss law, the surface will be closed one, and during this situation the total electric flux will be given as 1 upon epsilon times the total charge contained inside the surface S. Next is we consider a wire. This is wire, right? This portion is represented in the board line, while after that we have put the dotted lines. These dotted lines means that the length of the wire is infinite, right? Then to calculate the amount of charge, we introduce the term that is linear charge density. It is represented as lambda. Lambda represents the charge on unit length of the wire. So lambda is the charge on unit length of the wire. If you have the length of the wire is equal to L, then your Q will be product of lambda and L, right? And if you change the length of the wire to L prime, then Q will be lambda into L prime, right? So if you know the length of the wire, you multiply it with the lambda, you will come to know the total amount of charge present on that portion of the wire. So we want to calculate the electric field intensity produced due to this wire. For that, we choose a point P. This point P is at a perpendicular distance r from the wire, right? And one important thing is that the wire is positively charged, and we know that the electric field lines diverge outward from the positive charge. So the electric field produced due to this wire will be uniform, as the wire is uniformly charged. So it can be represented as equally spaced lines moving in the outward direction. So this will be the direction of the electric field. So the direction of electric field from the wire is in outward direction. Then we know that if we want to implement the Gauss law, we need to consider a Gaussian surface. So around point P, we choose an area element ds, right, such that the ds vector will be written as ds into n cap. This n cap is the normal to the ds, right? So n cap will be normal to ds. So we choose a Gaussian surface around P, right? So let it be a cylinder passing through the point P. So what kind of Gaussian surface we have chosen? We have chosen a point P of the observation, and a cylinder is passing through this Gaussian surface, right? So the condition is satisfied. You have chosen a Gaussian surface which is a closed surface and it is passing through the observation point P. This cylinder has radius r and length of the cylinder is L. As per the expression of linear charge density, Q will be written as lambda multiplied with the length which is involved inside the cylinder, right? So inside the cylinder, length L of the wire is used. So Q is equal to lambda into L. So Q is the total charge on the wire which is present inside the cylinder. So we know the value of total charge inside the cylinder, that is Q, and which is product of lambda and L. Now we know that Gauss law is phi E electric flux equal to surface integral of dot product of the electric field and the area vector. If we look at cylinder, it can be divided into three different regions, right? We have drawn the cylinder on 2 dimensions, but actually you know that the cylinder is a 3-dimensional object. If you assume a cylinder like this, the upper 2 portions are the circular one, right? And the remaining portion is curved portion. So we divide the entire cylinder into 3 regions. The first region is written as region 1. This is this much circular zone. The second is the region 2. And the third portion, region 3, is the curved portion of the cylinder. We know that the direction of electric field is perpendicular to the wire. So at this point the electric field is in this direction. For the region 1, the electric field is upward. Similarly, for the region 2, the electric field is upward, and for the region 3, the electric field is upward and the outward. Then we implement the Gauss law. Gauss law states that E vector dot ds is equal to Q in the total charge inside the cylinder divided by epsilon naught. So we know that A vector dot B vector can be written as A magnitude, B magnitude and cos of theta, right? So we use this thing over here. We write E ds cos theta. We have removed the vector signs. We are simply writing E and ds, and E and ds are the magnitude of electric field and the area vector into cos of theta. We split this surface integral into 3 different regions. Region 1, this one region, region 2, this particular region, and the region 3, this entire curved region, right? Then we examine our region 1. In region 1, the electric field is outward while the area vector has its normal in this direction. So the angle between area vector and the electric field is 90 degree. So theta is equal to 90 degree. The same thing will hold for the region 2 again. N cap is the normal to the area element and which is in outward direction. So the angle between the electric field and the area vector is 90 degree again. So theta is equal to 90 degree in region 2. When we make the observations in region 3, electric field is outward while N cap, the normal to the area elements in this region, are also in the outward direction. So electric field and the normal are in same direction. So angle between them is equal to 0. Theta is equal to 0 degree, right? So we apply this condition for region 1, this for region 2 and this for region 3 in the equation which we have written over here. So when we do so, cos 90 for region 1, cos 90 for region 2nd and cos 0 degree for the region 3rd. Cos 90 degree is equal to 0, right? And cos 0 degree is equal to 1. We know the values for the trigonometric angles for 90 degree and 0 degree. We put cos 90 0, so this term will vanish. We put cos 90 0, this term will vanish. Cos 0 is 1, so only one term will be there, that is EDS, right? We substitute cos 0 is equal to 1, so we will be left with EDS, so we write EDS over here. In the beginning, we said that the electric field is uniform. So it will come out of the surface integral. So it is EDS inside the surface integral, which is equal to Q in by epsilon naught. For the cylinder, area of the curved surface of the cylinder is given as 2 pi RH. We have used this expression in our mathematics, right? But here your height of the cylinder is exactly equal to the length of the wire, right? So we replace your 2 pi RH with 2 pi RL, right? So we substitute this thing over here. So as we are talking about the region 3 only, so we will be taking the curved surface area. We know that the total surface area is 2 pi RL plus pi R square. The surface area of these both circular portions. For that, the flux comes out to be 0. So we have neglected those zones. So we have E dot 2 pi RL is equal to lambda L divided by epsilon naught. We have substituted the value of Q in, that is lambda into L. A little rearrangement of the equation gives us electric field is equal to lambda divided by 2 pi epsilon naught into R. Observation is that electric field is varying inversely to the distance of observation point from the wire. So if you make a plot, when your observation point is very close, means the R is nearly 0. At this point, your electric field is maximum, right? As you keep on increasing the distance of observation point from the wire, means you are moving toward this axis, right? Your value of electric field will fall down, right? More is the distance of observation point from the wire, lesser will be the electric field intensity. Now, there are two situations. The wire can be positively charged or the wire can be negatively charged, right? If your wire is positively charged, it means that the total charge density is going to be positive, lambda greater than 0, right? So direction of electric field at every point is radially outward in that case, right? So direction of the electric field will be outward from the wire, right? If your lambda is less than 0, it means your wire is negatively charged. During that case, your lambda will be less than 0. So the direction of electric field at every point is radially inwards. Now we do a simple numerical to understand the things. An infinite line charge produced a field of this much, means this is the value for the electric field, that is 9 into 10 raised to power 4 Newton per coulomb, right? How these units come for the electric field? We know that force can be written as Q into E. Force can be written as Q into E. If I want to calculate the units for electric field, they will be force divided by the charge unit. So it is Newton, the units for force, coulomb inverse are the units for charge. So this is the amount of electric field, and Newton and coulomb both are the SI units. So no conversion is required. So you have an observation point at a distance of 0.02 meters. So this is the wire and your observation point is at a distance of 0.02 meter. Meter is again SI unit, so no conversion is required. You are supposed to calculate the linear charge density, right? You are supposed to calculate your lambda, right? We implement this equation. You just learn this equation. You will be using this equation again and again, right? It is very simple to learn this equation. If you restate this equation as 1 upon 4 pi epsilon naught, that is the constant term which we use during our Coulomb's law. 1 upon 4 pi epsilon naught, at the upper you put 2 lambda by r. This is the easy way to learn this equation, right? 1 upon 4 pi epsilon naught will be always in your brain, right? So it is 2 lambda by r. So we use this equation over here, right? We multiply and divide by 2 because we know the value of 1 by 4 pi epsilon naught. We want to use that value. So we multiply and divide by 2 on the both sides. We keep lambda on one side and other all terms on the other side. Then we substitute the value of electric field that is provided in the equation, that is 9 into 10 raised to power 4, and 1 upon 4 pi epsilon naught is equal to 9 into 10 raised to power 9. right? Here we are substituting the value of 4 pi epsilon naught, so we take reciprocal multiplied with 0.02 divided by 2. This term 2 has come from the rearrangement, right? So lambda comes out to be 10 raised to power minus 7 coulomb per meter, right? Lambda was the linear charge density, right? So lambda was q by l. So lambda was q by l. So q has units of coulomb, length has units of meter, so its units will be coulomb per meter, right? Just for the information, I am telling you that the surface charge density is represented as sigma, and it has units of coulomb per meter square, right?